Hello! Welcome to GARTC Videos, your daily supply of solutions to engineering problems. Again, if you like what you see, don't forget to subscribe and hit the bell icon so that you will be notified every time we have new videos. Today, we will discuss bolted connections per 2015 NSCP, which is based on AISC. Okay. So in this video, we will discuss the following. We have the gross area yielding, net area rupture, bolt shear strength, and then bearing at bolt holes, and also block shear strength. Okay. So these are found in the tension member and the bolted connection part of the code. And by the way, as we discuss this problem, I will also be navigating on this website. So this is our new website, gertc.online. gertc online. So here we have here useful references. So medyo hindi pa masyado maraming nilagay namin dito, but uunahin ko yung steel design here. So navigate here, steel design. We have here the basic code requirements, definition of terms, and so on and so forth. No? Kailang factors, we have useful tables, nandito lahat. Makikita nyo dito. No? So we have here, if you navigate here, we have mga properties of roll shapes. You can also find it here. Very convenient. Especially ngayon na most students are nakaharap sa gadget nila. So this is phone friendly, or this will just adapt to the display that you have. Okay, we have tension members and so on. So we will be navigating on this code as we discuss this video. Alright, here is our problem. The W150 by 24 tension member is connected as shown in the figure. So we can see here, this is our tension member, the white flange shape. So connected to, let's say, a column by means of 12 bolts. Alright? 12 bolts on gusset plates. So we will just assume here that the connection of the gusset plate to the column is adequate. Okay, these are the different data. So the bolts are A3 to 5 with threads excluded from shear plates. We will be discussing that later on, especially the code requirements. Okay, the bolt diameter is 16 mm. The hole diameter is 18 mm. The gusset plate thickness is 12 mm. Gusset plate, dalawa. And then our steel is 836, so your Fy is 248 MPa, and our Fu is 400 MPa. The distances S1 here, this S1 here is 40 mm. 40 mm. S1, S2 is 80 mm, and then S3 is 30 mm. This is also S1 here. Okay, and the properties of the wide flange section, W150 by 24, area is 3060 square mm. The depth, okay, we know that one. This is our total depth. The depth is 160 mm. The flange width, all right, this is our flange width, 102 mm. The flange thickness is 10.3. The web thickness is 6.6 mm. So we will compute the design and allowable strengths of this member based on all possible modes of failure which I have discussed a while ago. Right? So tension on tension yielding on gross area, rupture on net area, block shear strength, bolt shearing strength, bearing strength, and so on. Okay? Alright, so let's have the first part based on gross area yielding. Gross area yielding. I will be doing this in this part, gross area yielding and net area rupture. So what does the code says say about this. Okay, so we can find that here. Let's go to that. You navigate on this tension member, or you can find that here in the menu, steel, and then tension members, or you can just click it here at the topic navigation block. So we have tension. Well, of course, the basic concept of tension members is stress. The basic concept of stress, no, is force over area. P is the applied load, and A is the cross-sectional area normal to the load. That's the basic. Okay? And these are the code requirements. So regarding slenderness limitation, there is no maximum slenderness limit for design of members in tension. But here we have the user note. For members designed on the basis of tension, the slenderness ratio preferably should not exceed 300. This suggestion does not apply to rods or hangers tension. Anyway, so here, this is the tensile strength requirement. So the design tensile strength PPN and the allowable tensile strength PN over omega in tension members shall be the lower value obtained according to the limit states of tensile yielding and the tensile rupture on net section. So the design strength is PTPN and the allowable strength is PN over omega subscript T. So for tensile yielding on gross section, the nominal strength PN is the product of Fy and Ag, where Ag is the gross area of the member and then Fy is the specified minimum yield stress of the type of metal or steel, being the reduction factor for LRFD is 0.9 and the factor of safety for ASD is 1.67. So Fy times A sub G. Alright, here it is. So very simple. This is a very simple computation based on gross area yielding. P is 0.9, omega is 1.67. Alright, so the gross area here is the area of the channel or of the white flange itself. The gross area is 3,000, this one here. Use the pen. Okay, 3,060 square mm. That is our gross area. Okay, so and again, according to the equation 504-2, this equation here, 504.2-1, Pn is equal to Fy times Ag. Fy times Ag, so Fy is 248. Or Fy, that will be here. Okay, Fy is 248 and then our Fu is 400 MPa. Okay, let's substitute the values. Okay, you just do the substitution, okay? I hope you don't mind. Your Fy must be in megapascal. This must have a unit of megapascal and your Ag must be in square mm. The resulting unit here, we know that will be Newton. So you just divide the result by 1,000, you will get kilonewtons. So that is our nominal strength. So finally, we can now compute the design strength and the allowable strength. So let's go back to the code. Alright, this is the code, what the code says. The design strength is a product of P and Pn, and the allowable strength is Pn over omega. Right, so our design strength LRFD is equal to Phi times Pn. Our Phi is 0.9. This is our Pn, so the result is 682.992. And by the way, how do we use this? So just like for example, ito yung this is the requirement, the core requirement. The factored tensile load must not exceed the design strength. The factored strength must not exceed. For example, if your combination is only due to dead and live, your Pu is equal to 1.2 Pd plus 1.6 L. That's how you apply this design strength. Factored load must not exceed the design strength of the. Alright, next, the allowable strength. okay, ASD is equal to PN divided by omega. Omega is 1.67 and this will give us 454.419 kilonewtons. Okay? Kilonewtons. So for example, how do we apply this? So the requirement is the total load must not exceed the allowable strength. The total load, if you have dead and live, for example, is just the sum of dead and the live. You don't apply the load factors here. So for ASD, dead and the lives, PN over omega. Okay? And by the way, talking of these load combinations, you can navigate sa website natin. No? So you can click here the basic code requirements, or you can go here online reference, structural, steel, and then basic code requirement. So for the basic code requirement, we have here the load and load combination, or you can click it from here or from here. Load and load combination. Alright, so these are the different symbols, annotations. D for the dead load, E for the earthquake, and so on and so forth. For the LRFD combination, for D plus F, F is the load flow due to fluids of well-defined pressure, 1.4 D plus F. For dead, okay, dead and live, 1.2 dead, 1.6 live. Okay, you can navigate on this. This is for LRFD, and this is for ASD here. Load combination using ASD. Dead and fluid, dead, live, fluid. H is lateral pressure, and so on and so forth. This is applied, okay, this part here is for the ASD, and this is for the LRFD. Alright? So, what I just shown you is an example if we have a dead and live combination. Alright? So, this is the first possible mode of failure. That is the gross area yielding. The yielding of the gross area of our wide flange section. Okay. Now, let's have the other part. Okay. The other mode of failure. Based on net area rupture of the W section. Okay. Net area rupture of this wide flange section. So, what did the code talks about this provision here? Okay, let's go back. Okay, so here it is. For tensile rupture on in the net section, Pn is equal to Fu times Ae. Okay, what are these? Fu is the specified minimum tensile strength of the type of metal. In our case, it is 400 MPa for 836 steel. And then Ae is the effective net area. Effective net area. Alright, so talking about net area here, okay, just scroll down. The effective net area is the product of the net area AN and the shear lag factor U. Medyo mahabang usapan to. We will be discussing this in this video. Alright, shear lag factor. Okay, let's go back to our discussion first. So, this is it. Our P is 0.75 and our omega is 2. Take note of our factors here. Go back here. Okay, P is 0.75 and omega is 2.0. So, where is that? Which part? The net area rupture. Saan part yan? In what section? Okay. It will be here in the frontmost. Okay, this is the load. The frontmost bolt. If you cut as a plane here, it will look like this. Alright? This is our net area. This dark colored portion here. Okay, so the net area will be the gross area, and then we will subtract the bolt holes. Not the circle, but this hole here. This part here. That part. And this part here is the effective diameter of the hole. Alright, let's talk about it. So, effective hole diameter. The effective hole diameter is the actual nominal hole diameter plus 2 mm. Okay, Our basis to that, for that, is this one here. So, net area determination. So, according to this, the net area of a member is the sum of the products of the thickness and the net width of each element computed as follows. And according to this, in computing the net area for tension and shear, take note, for tension and shear, the width of the bolt hole shall be taken as 2 mm greater than the nominal dimension of the hole. If this is our bolt here, this blue colored here, and then this is our hole, DH, the effective will be the hole diameter plus 2 mm. Plus 2 mm. Alright? Now, in our problem, I just gave you the hole diameter. It is given, the hole diameter was already given here. The hole diameter is 18 mm. 18 mm yung ating hole diameter. But, just in case, you wonder, what is our reference? Is there a limit for this hole diameter? The hole size? Okay, let's see from the code. Okay? Alright, you can navigate here. Go to bolts and threaded parts. Okay? Or you can click it from here. Sorry. Lost it. Okay. Bolts and threaded parts. So these are the sizes of holes. You can take it from here. Okay. Sorry. Alright. Sorry. This one here. Not. Okay. Basic code requirement. Bolts and threaded parts. So we have here the hole sizes and use of holes. The maximum size of holes for bolts are given in this table. Maximum, take note, maximum. For bolt diameter 16 mm, M16, the standard diameter, hole diameter is 18 mm. Oversize is 20. This is the maximum, okay? You can make it 17 if you want. Not just more than 18, no? So for 20 mm, 22 mm ang standard. And then the oversize is 24. This is for the slots. This column here for the slot. 22 mm, the standard diameter is 24. You can make that 23. No, not 23. Yes, 23. If important is it should be larger than this. Because you can hardly fit that bolt onto that hole if you will have exactly 22 mm. Of course, common sense. So here, our 16 mm, I just used the maximum size, 18 mm. Right? So our hole is 18 mm. So we have 18 mm plus 2 mm. Okay, so that will give you 20 mm. The whole size is 18. This is given in the problem as 18 mm. Go back here. Go here. 18 millimeters. Okay, so let's call that the effective hole diameter. Effective hole diameter. So the net area will be equal to the gross area minus 4 na holes. 4 holes. The hole is equal to the diameter effective times the thickness of the flange. So that will be AG minus 4 times the... Okay, that one times 4. Because there are 4, no? So only this part here, the bolt diameter, the effective hole diameter part here, times the flange thickness. Okay? Times 4. 1, 2, 3, 4. So this is our net area. Alright? So the net area is 2236. And then the effective net area is equal to the product of U and AN. And that can be found here. Okay, let's navigate it dito sa tension members natin. Tension members. Okay, effective area. Effective net area is AN times U, where U is the shear lag factor, which you can find it from here. click that button. By the way, you can just open this grtc.online and you can navigate all this inside. Okay, we have this one here. Actually, case 2 or case 7. Let's do first case 7. According to this, for W, M, S, or HP shapes or T's cut from these shapes, and then with flanges connected with 3 or more fasteners per line in direction of loading. Okay, when BF is more than 2/3 D, the shear lag factor is 0.9, and when BF is 2/3 D, the shear lag factor is 0.85. Okay, let's discuss that one. Alright, so this is it. Okay, flange. Okay, what is meant by this? With 3 or more fasteners per line in the direction of loading. Okay, this is our loading. And then this is our, we have 4 lines here. One line, another line in the direction of loading, and another line at the back. And on that line, along that line, there are 3 fasteners. So this is qualified. We are qualified to use this portion here. All we need to evaluate whether if BF is greater than or less than 2/3 of the D, where D is the depth of our wide flange. Okay, this is our D, and of course BF is the flange. Right, so 2/3 of the total depth of the flange is 160. Our D is 160. That is given here in the property. 160, our BF is 102 mm. 102 mm. So this is it. 2/3 of 160 is 106.667. Our BF is 102. So we can see here that our BF is less than. Our BF is less than 2/3 D. So meaning we will use the 0.85 as our shear lag factor. Okay, that's it. Then finally, our effective area is equal to U times AN. U times AN, our U is 0.85 and our AN is 2,236. That will give us 1,900.6 square mm. Finally, we can now compute the nominal strength. Nominal strength, FU times AE. FU is 400 MPa and this is our AE. Substituting the values, we get 760 kilo. Then our design strength is VPN. Our P is 0.75. Okay? And our allowable strength is PN over omega. Our omega is 2. PN over omega. Okay? That's it. VPN and PN over. Again, to apply this one, this shall PU must not exceed this value. And PA, allowable load, or the given load or service load must not exceed the allowable. Alright. Now, notice this portion here. Okay. According to this table, part of the table, if U is calculated per case 2, the larger value is permitted to be used. Okay, what is that? Case 2. If U is calculated per case number 2. Okay, now let's go back to this table. We have used case 7. So if you will use case 7, then this is it. Okay, you may ask me, how about if there are only two bolts? Then we cannot use this case 7. 2 bolts per line. Right? Then you will go to the basic. We have here case 2. Case 2 is computed as U is equal to 1 minus barred X over L. What is barred X and what is L? Now, for our connection, this is it. Okay, this is our gusset plate. The contact surface connected part is here. Our barred X is the distance from that part to the centroid of this. So, in the case of wide flange, we will cut it into 2. And then we will locate the centroid of this half wide flange and the distance from the connection. Okay? So, we can go back here. Okay. Part X is the distance from the centroid of the connected area to the plane of the connection. Alright, as what I have explained here. The centroid of the connected area, this one, which is half of the wide flange, to the plane of the connection. That is our barred X. Right? And our L is the length of the connection. Go back. In the case of bolted connection, okay, example lang, this is it. Angle or wide flange, this is our L. Or in this case, our L. That's welded, that will be our L. Take note, L is the length parallel to along the line of the load. Parallel to the load. Alright, so this is it. Part X. So to use that, we will cut our wide flange into two. And then we will locate the centroid of this area here using, of course, Varignon's theorem. Okay? I can do this fast. Our D1 here, let's compute our D1. This is our total depth. So our D1 is the half of the total depth minus the flange thickness. That's our D1. Our area of this, okay, the area of this half is 1/2 of the total area. 1/2 of the total area. The total area is 3,060. So that will be 1,530. So our barred X using Varignon's theorem is this one. I'll just explain. D1 times TW is the area of this. And then this one here is the distance of this centroid from the bottom here. That will be TF plus half of D1. Right? And BFTF is the area of this flange. And then 0.5 TF is a centroid of that measured from the bottom, from this. Because this is the contact surface of our connection. This part here. Okay? Our connection surface is here. Remember the definition of our barred X. Distance from the centroid of the connected part to the plane of the connection. This is the plane of our connection. Okay, para klaro. Okay, yun. And this is the centroid of the connected part. We just cut it into two because there is also a plane, a connection here. Alright, so this will give us 17.11. Then we can now compute our U. Alright, our U is 1 minus barred X over L. This is our L. This is our L, which is equal to 2 times S sub 2. Okay, S2 is, okay, let's go back to the given here. S2 is 80 mm. S2 is 80 mm. So 2S2 is 160 mm. So we can now compute our U. Now notice, this gives us 0.893. The one we used before is 0.85. Now, according to the code, we can use the higher value if we will use this case number 2. So we can use that actually. We can use that value. Can we use the previous one, kanina? Yes, you can. It is much conservative than this one. But you are allowed to use this value. So using that, we can get the other values, the design strength and the allowable strength. Again, just an example, we can how do we apply this design strength? This is it. Example, if you have combination of dead and live only, so PU must not exceed PPM. And for the allowable strength, P must not exceed the allowable strength, where P is equal to PD plus P. Just an example for the dead and live combination. Alright? So, that's it. We will cut this part. It's almost 30 minutes. Alright? So, and by the way, before I end, let me also introduce you with this website. We have just launched our new book. Just click on this link menu here, GRTC Books. And temporarily, we can transfer you to this website. Just click this link. Alright? This is now ready. Available na to. Today is May 13. So, practice problems in civil engineering. Alright? And you can order our books sa Lazada. So, official Lazada book namin, genuine DITG books. You can order it here. Right? Redirecting to Lazada. Okay? Ito yung genuine. Yung ibang ano dito, marami kasing mga pirated sa selling in Lazada. So, these are all genuine. Okay? So, that's it. By the way, talking of our book, so you can find the details of this book. We have here the preview of what is inside. And by the way, sinadya namin na merong mga gray background to minimize, at least to discourage piracy. And these are our other book. Alright? So, okay, so that's it. This is part 1. We will continue the other failure mode of failures on our next video. Okay, thank you so much, and I hope you learned a lot from this video. Thank you.